We use these things every single day, but what is actually happening inside that box on your desk? Well, today, we're going to pop the hood and see how your computer really handles information at its most fundamental level. Because look, if you want to protect your data, you've got to understand the machine first.
And that's really the core question, isn't it? Our photos, our private messages, all of our work, it's all just data. And if we don't get the basics of how it's stored and processed, well, it's kind of like trying to guard a house when you don't even know where the doors and windows are.
So whenever you click your mouse, type on your keyboard, or even talk to your device, it doesn't understand you in the way a person does. No. It translates every single one of those actions into the only language it speaks, binary. It's just a massive, massive stream of ones and zeros, representing tiny electrical states of on or off. That's it.
Okay, so to make all of this make sense, let's use an analogy. Let's think of your computer not as some magic box, but as a very, very busy kitchen. And in this kitchen, there are 3 key crew members who are running the entire show.
First up, we've got the CPU, the Central Processing Unit. This is our chef, and this chef is incredibly fast. We're talking billions of commands every single second. But here's the catch. The chef is also incredibly forgetful. It has no long-term memory whatsoever. It just follows the recipe, the instructions for whatever it's doing right now, and then it's on to the next thing.
So where does the chef do all this work? Well, that's the RAM, or Random Access Memory. This is our kitchen countertop. When you open a program or a file, it's moved from storage onto this countertop because it's super close and can be accessed in literally nanoseconds. It's the temporary workspace for everything you've got going on at the moment.
And finally, we've got the pantry. This is your hard drive or your SSD. This is the long-term storage where all your files, your applications, and the operating system itself just kind of sleep until they get called up. Now, it's a bit slower to get things from the pantry, but that's where everything is kept safe for the long haul.
So let's just put it all together real quick. The chef, our CPU, grabs ingredients, which is our data, from the pantry, our storage drive, and puts them on the countertop, the RAM, to work on them. That's the flow. A really efficient computer is just one that minimizes those trips back and forth to the pantry. And that's exactly why having enough RAM, a nice big countertop, is so important. Okay, but who manages this whole chaotic kitchen, right? Who keeps things in order? That would be the operating system. Your Windows, your Mac OS, your Linux. Think of it as the restaurant manager, the bouncer at the door, and the accountant all rolled into one. It makes sure everything runs smoothly and that everyone follows the rules. Let's see how that works in the real world. Say an app wants to open a file or use your webcam. It can't just do it. Nope. It has to ask the operating system for permission. The OS acts as the bouncer. It intercepts the request and checks the app's permissions. If it has the right credentials, great, go ahead. If not, access denied. This whole system is what prevents some random game you installed from reading all your private emails.
And this is exactly why the holy grail for most malware is something called privilege escalation. A malicious program will try to trick the OS into giving it more power. It's essentially trying to promote itself from being a regular user to being an administrator, so it can just waltz past all those security checks.
I mean, this is why you hear it all the time. Running a program you don't trust as an administrator is so, so dangerous. It is literally like handing a total stranger the master key to your entire house. You're telling the OS, hey, this program, let it do whatever it wants. Let it go into any room, open any drawer. It's just a massive security risk. But wait, the security doesn't just stop at the software level. It goes deeper. The actual physical parts of your computer, the silicon chips themselves, have their own little fortresses built right in, all designed to protect your data.
2 of the key features here are memory isolation and secure enclaves. So memory isolation is kind of like putting up little dividers on our kitchen countertop, the RAM, so your web browser can't peek over and see what your password manager is doing. A secure enclave, though, that's even stronger. Think of it as a tiny, locked-down vault inside the chef's office, the CPU, where super sensitive stuff like your fingerprint data gets processed in complete and total isolation.
But here's the twist. Even these hardware fortresses, they aren't invincible. You might have heard of these huge vulnerabilities called Spectre and Meltdown a few years back. They were such a big deal because they proved that really clever attackers could find cracks in the very foundation of the CPU's design. So how on earth did they work? Well, to be faster, modern CPUs are always trying to predict what you're gonna do next. Spectre and Meltdown took advantage of this predictive behavior. Using our kitchen analogy, it was like tricking the chef into speculatively grabbing ingredients for a recipe he might have to make later, and in the process, getting him to read the labels out loud. It was a sneaky way to leak secrets from memory that was supposed to be protected. So you might be wondering, if even the hardware has flaws, how can we possibly trust our computers? Well, the answer lies in this really important process that happens every single time you press the power button. It's all about establishing a chain of trust. Think of it like a series of handshakes, or dominoes. It starts with the hardware, which is the unchangeable root of trust. The hardware then boots up the firmware, which uses a digital signature to verify that the operating system is legit and hasn't been tampered with. Then, the OS does the same for all your applications. Each link in this chain checks the integrity of the next one. If any link is broken, the whole startup process can be stopped to keep the system safe. And of course, this is exactly where attackers focus their efforts. They try to inject their malicious code directly onto the countertop, into RAM, to try and avoid being detected on the storage drive. They try to manipulate the OS to get those master keys through privilege escalation. They are attacking the very architecture we just laid out. And that's really the main takeaway from all this. Once you understand that flow from the pantry to the countertop to the chef, you can start to actually visualize where the security guards need to be. You can see why you need a guard at the memory gate, and another at the disk vault, and another one watching the CPU's control room. It stops being this abstract concept and becomes something you can actually picture. And you can see this for yourself. Seriously, open up Task Manager on Windows or Activity Monitor on a Mac and just watch. Watch your CPU and memory usage spike when you open a new app. You can even use tools like Process Explorer to see exactly which program is accessing which file. It makes all this invisible stuff visible. So, I'll just leave you with this question. Now that you've had a peek inside the workshop, you've seen the chef, the countertop, and the pantry. Think about the apps you use every day. Think about the permissions they're asking for. What do you see differently about the digital world now that you know a little bit more about the machine that runs it all?